Okay, one more time. Good morning, everyone. And yeah, right now we have about 22 students, or maybe including myself, we are 22 in the class, which is an okay number. And yeah, as I was saying before the start of recording, I like to keep it at that level. And the Department of Civil Engineering of UVic have asked me to encourage students to attend the class. And therefore, I'm requesting you guys do your best and attend as many classes as possible. Otherwise, we have like other tools like quick quizzes, etc., to keep that number. Any update on when Bright? Okay, yeah. Can you guys go there? Because last night I think I started Brightspace. So can you guys in the chat confirm that you can access Brightspace? Okay. Okay, yeah, it's there. Even I uploaded this slideshow that I want to present today. I'm happy that it's in there. Is the function, I think last year there was a function where you guys could create teams in there, like you created your team in there. Hopefully you guys can just do that and start with creating the teams for the project work. Outline, let me look at the outline again. Oh yeah, we have quite a few. I'm very happy. I mean, the department would be happy that there is interest in the students. Yeah. So we still have time, but hopefully by Friday, I can check with everyone and make sure that you guys have teams, because by next week, you should submit a work plan. Yeah, just email me if there are issues. Hopefully you can create your teams for the project in the next few days. And then if a few students have trouble, they can email me and I can introduce them to each other. And by end of next week, I'm expecting to receive some work plans. Okay, so any discussion or comments from the previous week or last Friday presentation? Okay, great. Let's try to get started here. I should remove these things, probably blocking your view as well. Yeah. Full screen mode. Yeah, let's see if we can continue like this one. I need one more person. One last check if anybody is in the waiting room. Ah, pretty good. Excellent. Okay, again, my name is Ali Rasek, and I am a senior engineer with the company HDR in Vancouver. I think HDR has a branch in Victoria as well. And so far in BC, they were more famous for architectural, but they are gradually building up their engineering departments as well. So maybe I think a lot of you guys are close to graduation. Maybe you should have HDR in your radar as well. And this session, in the first part of module 1, that's the way I named it, I try to introduce single degree of freedom dynamics to the class. Okay, already 11:05, let's get started. So here is the general idea idea of what dynamics of structures is. Dynamics of structures would be mostly the first two modules, as at least it's focused on dynamics of structures before we proceed to earthquake engineering, more like engineering side of earthquake engineering. Obviously, ground motions create the structural motions when earthquake happens. And the two top questions that a structural engineer who uses earthquake engineering or who uses earthquake engineering tools wants to know and use in the design is how much deformation we have in the structure and how much force was created in the different members, in different primary structure members, and also secondary structure and appurtenant. The schematics is here. So this is your typical two-story building in response to earthquake, and the ground motion shown here is the earthquake. And so here in this slide, I just wanted to just give you a high-level picture of ground motions that we deal with in earthquake engineering. We will have at least one full session on hazard. Hazard is mostly dealt, like the geotechnical engineers or geologists deal with hazard, but we should know some of the nomenclature there so that we understand the reports they give us for our work. The important ground motion characteristics are, one is magnitude. Magnitude means, what does magnitude mean? Magnitude, like in these pictures, is like the highest values that you see. Normally, we use acceleration as a measure of the ground motion, like we show this earthquake records as acceleration time histories, which is the most useful for structural engineers. And magnitude means the highest value in these plots, which sometimes we call it PGA, peak ground acceleration. Also, another feature which is important is duration, because some earthquakes are much shorter. A lot of like crustal earthquakes have shorter duration. And in like BC, we have subduction zone earthquakes, which sometimes like it's expected that they will take a few minutes. So, I mean, they have, like comparing magnitude and duration. Magnitude is like the level of force that the structure will see in a millisecond, which could be very large. Duration is about repeating, like the structure will see some level of force repetitively. In most of BC, say, crustal earthquakes are stronger, but the subduction zone earthquake is going to have very long duration. So the structure will see certain level of force once and again for many times. There is also frequency content. Geotechnical engineers, like they deal with that a lot, but for us as structural engineers, the most important issue is how the frequency of earthquake is related to the frequency of our structure. And if the major frequency of earthquake is very close to the frequency of the structure, we will see much higher response because it's like a dynamic effect. We will discuss this issue quite a few times during this course. Okay, so more on the frequency content. Complicated motions can be described as summation of simple harmonic motions of different amplitudes. basically what we are showing in this picture here. You have your earthquake record, like this is maybe 1 or 2 seconds of earthquake records, and it can be decomposed, maybe I can use that term, to summation of multiple sinusoidal curves with different frequencies. And the importance of this substitution, maybe they are equivalent, we can substitute one with the other, is that we can see which frequency causes has the highest amplitude. And that's the most important frequency. Again, as I said, geotechnical engineers are a lot more concerned with this issue. For us, the most important issue is that what is the most strong frequency in the earthquake, and how does it relate to the primary frequency of our structure. Okay, moving on. Yeah, because we will be dealing with dynamic analysis, which is different than a static analysis, which you guys should be familiar with. The dynamic characteristics of the structures are different, which pretty much means their frequency, their primary frequency is different. And it's like your acoustic music tool, like your guitar, which has like different frequencies depending on the length of the what you tie in there, and different structures with different material and different heights, they have different frequencies. So each structure has its own signature dynamic characteristics, and on top of the list is the frequency. And that will dictate the response of the structure to the earthquake and ground motion. That we will gain some familiarity with this issue through this term, and maybe you can build up on that later on or in more advanced courses. Because this session is focused on a single degree of freedom structure, here I have shown a portal frame, and the portal frame is its response or its behavior is almost 1 degree of freedom, single degree of freedom. Say this portal structure has regular columns and a very rigid roof in a way for this structure. Therefore, the roof won't deform much, and pretty much the only detectable deformation of this structure is in the sideways, the displacement that is shown here. There might be other deformations, but they are relatively small, and we can pretty much deal with this portal frame as a single degree of freedom structure. And one important characteristic of this structure is its stiffness, which means when I apply a force to the structure, how much displacement I'm seeing. As the material in this structure is mostly linear, we assume it's mostly linear or close to linear, and we don't have huge deformation. The expectation is that the relation between force and displacement is linear, and we have a single value of stiffness, which is good enough assumption for most of our work in structural engineering. Again, the force is applied, and the response is displacement, and stiffness varies when we change the dimension of the frame or the material cross-section, And also even if we change the connection type, say from one extreme, which is a fully rigid connection, to another extreme, which is pinned connection, there will be a major change in the response. And most structures are something in between, but we can idealize connections as being rigid or pinned, or maybe in between if we want to say model them as springs or something. And yeah, so we covered this sheet. We can move on. Mass is also important. Mass of the structure. In this case, in the case of this portal frame, the most of the mass, big amount of the mass is in the roof. So mass also is important in the dynamic response. For this structure, earthquake ground or earthquake acceleration is applied at the base. However, equivalently, we can assume that there is a very, like the force is applied to the mass. And we will talk about this a few times. This is not even a simplification. They are like exactly equivalent. Having acceleration at the base is exactly equivalent to having this force applied to the mass. And responses of interest is identical between the two, but therefore we do that a lot. We, like, sometimes as a student, it could be confusing even for me why we are talking about ground motion and then we apply a force. We will show it once and again that these two concepts are identical. So the structure will respond to the earthquake force, and the response that we are seeing, like variation of displacement with time, is affected by the stiffness. We already discussed what stiffness is. It's affected by the mass. Here we said most of the mass is concentrated at the floor level, here at the roof level. And there is another parameter that we call damping. The most materials and hence most structures, they damp energy, meaning that if you start some motion in that structure and you wait long enough, that motion will go away or it's damped out, dissipated. These are different terms that we use in describing damping. And again, we will discuss damping a lot more throughout the term and today. Now, back to what I already mentioned, like sharing or replacing the base motion with a very varying force at the mass level. It's exactly equivalent. There's no simplification in there. However, there is a simplification which is very popular within structural earthquake engineers and is implemented in National Building Code of Canada as well, which is replacing the replacing the varying force with a constant force, which in a way that constant force represents the most critical response we expect in the structure. We will discuss this a lot when we get to the National Building Code of Canada in the 5th or 6th session. So as I said, in most building codes, including National Building Code of Canada, we use equivalent lateral load, which is like a load which is not changing with time. And we expect to use that loss for a proper design, which is very successful. It's a very successful idea and helps with a quicker design comparing with the time history and also correct design. Even I can exaggerate and say more correct than Raj dynamic analysis. So if the engineer doesn't think carefully about his dynamic or their dynamic analysis, their estimate would be worse than using the simplification by National Building Code of Canada. This is what it looks like. You guys will, as earthquake engineers, will use this equation a lot, and we will be discussing it further during the course. And generally, the main parameters here, if I can recollect them well, is the a spectral acceleration that the code provide for different regions of the country and different cities in BC. MV is probably the correction factor, which accounts for higher modes. I is famous as the importance factor. W is the weight of the structure. And we have used two reduction factors, one to account for ductility and one to account for overstrength. We will get back to this a few times, especially when we introduce you to the National Building Code of Canada. Now, taking one step back and looking at what, in the science of dynamics of a structure, what they mean when they are talking about a single degree of freedom a structure. It's basically a combination of mass. So there is a mass. I showed you the mass in our structural model. There is a stiffness, which certain a stiffness. There is damping, which damps out the energy. And there is a loading function, which changes with time. And the response that happens is also changes in time. It's like the deflection that changes in time. And in structural engineering, we are interested in the forces in this member, which is our beam and column and anchors and foundation and whatnot. So we are interested in the forces that happen in this member, in this spring. And those forces help us with the design. Again, back to our portal frame, which is the single degree of freedom system here. As I said, most of the time, say in this portal frame, the IB, which is the beam's rigidity, is higher, not only because of the beam, but because the flooring system is a lot of times rigid, and we have slabs, and say concrete slabs or wooden slabs, etc., that really makes this floor rigid. And most of the response is dictated by moving the frame right and left in this picture. And so a lot of the stiffness of the system would be dictated by the column stiffness, which here we have shown as or is controlled by EIC, the elastic modulus of the column, multiplied by I of the column, which is the section property of the member. So I think in your other structural analysis courses, hopefully you had one, you have been able to estimate the stiffness of this structure. I think, yeah, this one of the examples that we walked through last year I can repeat that process. However, yeah, I mean, before getting into dynamics, you should maybe pull out your notes from the previous course, etc., and try to repeat that process. You have this structure, maybe with a rigid floor or maybe not a rigid floor, and you try to see what is the response of this structure to the lateral load, the same as I showed here or here. So there is a lateral load and there's displacement. You can plot this, and we don't even need to plot because it's a constant value. You should be able to estimate the stiffness of a portal frame. That's maybe a basic exercise for people who want to have a career in structural analysis and design. You should have an awareness of that, or be able to find an example and repeat it, or maybe some young people can do it like from their mind, just do it on the paper. I can find my sources. Therefore, again, back to the discussion that we are simplifying the portal frame as a single degree of freedom, and a lot of times the flooring is really rigid, but sometimes it's not. You can compute the stiffness, and yeah, as I said, maybe you can pull out an example and carry it with you, or some people, I would say when the young people, they just in a few minutes, they create this model in some software and they obtain the stiffness. That's also acceptable, but general awareness that there is a stiffness in this structure, and you guys are fourth-year students who are interested in structural engineering, so you should be able to, in one way or another, quickly estimate the stiffness. And in a lot of the work that we do as a structural engineer, structural engineers, we assume that everything is elastic and we find a single stiffness value. Again, now repeating ourselves on the response to dynamic load. And so a lot of times we assume that the mass is concentrated at the roof level, and sometimes you will see this once and again that we use the roof mass plus half of the mass of the columns and walls, etc. And we assume that all that is concentrated within the roof, which is a good enough assumption for our work. So that's the mass of the system. You see two masses. One was showing the initial location of the mass, and the other one after the movement. The viscosity, just for presentation purpose, it's shown like this. It doesn't look like that. So it is not bracing. Even the last year I was preparing this slideshow, I was copying this from books, and I thought, oh, are they showing a bracing? No, this is not bracing. This is just for schematically showing the viscous damping that gradually will dampen the system. Displacement is the most important response, I think. However, the structural engineers always look for forces. Velocity is the speed with which the mass will move. And the acceleration is change of velocity with time. We normally apply acceleration at the base, and sometimes we are interested in the acceleration of the mass, which is acceleration of the mass is important because it's an indication of the force, like mass multiplied by acceleration is force. So a lot of times as we as structural engineers, we talk a lot about acceleration and displacement. We overlook velocity, while a lot of geologists, they are interested in velocity of ground motion for different reasons. It shows whether they are close to the rupture or not, and they have their own discussions. And inertia is important. Inertia is dependent on the mass of the structure and the acceleration. That's the force that will be created in the system. And that's a certain definition I have maybe copied from sources, but a lot of times if I myself say inertia, I only mean mass. Depending on the context, sometimes means mass multiplied by acceleration, sometimes it only means mass. Damping, we already discussed, and the phenomena that causes damping is also velocity. So damping is normally like damping ratio multiplied by velocity, but we don't get into those calculations in structural engineering. Let's move on. This is a very important dynamics equation, and I guess, not very sure, but I know that some of you guys or many of you guys have taken a course in dynamics. That's not very important. A static is a lot more important, that you could handle some general analysis, a structural analysis in response to a static loads. So what are the forces that are applied to the structure at an instant of time? The obvious one is the external force here, PT, in this dynamic setup, assuming that there is a force applied here. However, back in our mind, we know that it's an equivalent. But let's assume that the force is really applied here. Obviously, this force is there, P versus P. Two other forces that are more subtle in a way is the force that is caused by the response of the spring system, Fs. A spring or a stiffness comes from the columns or even the beams. And there is a damping force, which is a little bit more subtle. And as the structure deforms, it dissipates energy, which is equivalent to a forcing function, a damping force. And again, reminding myself, this is not bracing, this is just a representation of viscous damping. So now that we have all the forces, we can write Newton's second law of motion. All the forces applied of the structure and the mass, we assume that all the mass is concentrated here. All the forces that are applied on a mass, they cause acceleration. So we know what are the forces. There is this external force, there is the damping force and a spring force, and they cause acceleration. Or some people are different depending on which dynamics books that you look at. Some dynamics books or some, say, older engineers, us, we look at this term as an inertia force. And sometimes we just write the balance of all forces, and one of them is inertia force. Other people look at it differently and say inertia force is not really a force, and all these forces have caused movement. So, but both a school of thinking result in the same outcome or same equation. And normally we regroup the forces, or like take this term to the other side, because we are interested in everything external force that we really know that is applied, and all the responses in terms of acceleration and damping and spring deformations. So that's all you need to know in dynamics. So if you have taken a course, probably you have spent a lot more time on this dynamic equation or solution, but that's as far as what we need in this course. Again, same equation from the previous page. And now we know that in linear material, like the spring force is a function of displacement, and in a linear damping, the damping force is a function of velocity. Therefore, we can rewrite this equation here. Now, the importance of this equation is that on one side, on the right side, you have the forcing function, and on the left side, you have the displacements. It's good to be aware of this equation for all of us to know that the response consists of inertial force and damping force and stiffness force. It's very important, but normally we use different software, say SAP 2000, to really resolve this equation. Or in special cases, you guys might know MATLAB and other more sophisticated tools that can help you solve a differential equation like this one. So yeah, as I said, so we solved the differential equation here to obtain the displacement as a function of time. That's the ultimate purpose of dynamics of structures. Now let's see what free vibration is. Let me check the time. So you're 40 minutes in. It's a good time if you guys have a comment on details or high level telling me that I'm talking too fast or it's not, you cannot hear me well, etc. Or about the details of these equations. Yeah, but as I said, I mean, as engineers, we should high level understand this, yet be aware of these things, but it's not exactly your day-to-day work to use these equations. We can move on. Free vibration. So what does generally free vibration mean? Every single degree of freedom system, now we showed another representation of a single degree of freedom system. It's something that the structural engineers, civil engineers would work with. Often towers which have like a water tank on top. So you have a tower, a structural system, and here you have a tank which is full of water. This is another good example of a single degree of freedom. Basically, what the argument here is that the vibration of this structure has some basic characteristic way. Like if you start some movement here based on like a very, very short duration, earthquake happens, and then the earthquake finishes, there's no forcing function. This structure will keep on bouncing right and left. And the way it bounces back and right and left, as we already discussed, no surprise to us, it's dependent on the mass, on the stiffness, and on the damping. So again, if the structure is disturbed one way or other, or maybe there's like a very, very strong wind for like half an hour or something, and then the wind finishes, the structure will keep on moving without a forcing function. so there is an initial movement caused by wind, earthquake, something hitting the tank, etc. And these parameters will determine how this structure will keep on moving, starting from the initial displacement and moving forward in time. Period of a structure is a very important characteristic of a structure, assuming that no damping happens in the no dissipation of energy happens in the previous structure or in the portal system here. This structure can keep on vibrating forever. The reason that it stops vibration is because of energy dissipation. And it takes certain amount of time for a back and forth, like starting from zero movement, going to right, and then moving back to the left, and then going back to the previous position, like from A to E, which is identical, both in terms of displacement and direction of movement. This amount of time is period of a structure. Very, very important characteristic of a structure is its period. And so during free vibration, the structure will oscillate through cycles with a fixed time, which is period. I didn't mention that there shouldn't be damping there, but without damping, if there's no damping, this will go on forever. But even if there is damping, like we have small values of damping ratios, this will happen, but the amplitude will gradually reduce. Period could be calculated to be this equation, function of mass and stiffness. Yeah, even after so many years of using these equations, I keep on forgetting whether it's, like if somebody asks me, I say I can't remember whether it was 2 pi multiplied by a factor or 1 over 2 pi multiplied by a factor. So I have to look at my books. However, something that I really like you guys to kind of memorize, try hard to memorize, is that period increases with mass. So it has direct relation with mass, and it has a reverse relation with the stiffness. That's a good thing to memorize. So when it happens once and again, that you should make a judgment about design of a structure and its mass is increasing, you should say, okay, because my mass is increasing, the period of my structure is increasing. That's something to memorize. And the stiffness is reverse, and you should be able to make a quick judgment, saying maybe by the end of this course, or maybe after a few years into your career, if you are an earthquake engineer, you should make that judgment that, okay, because my stiffness is increasing, I'm adding more bracing, therefore the period of my structure is going to reduce. That's I think it's maybe 1 out of 10 things that I'd like you guys to really memorize in this course. That adding mass will increase your period. Frequency of the structure is the reverse of period. And there's another concept, angular frequency, which is multiplying frequency by 2 pi. So as I said, yeah, that 2 pi comes in numerator or denominator, and I could never really memorize it. But I keep on using this fact as an earthquake engineer, that when I have higher stiffness, I have higher frequency and lower period. All right. Next slide. Again, showing our equation of motion that we previously obtained. However, as I said, the forcing function is gone. The structure is not really seeing any forces, and it's gradually damping out because this is damped free vibration. So the amplitude is gradually reducing. that's the most of the structures that we know are what we call here underdamped. Like a damping ratio of 0.1 is very, very high. So steel has a damping ratio of about 2%, like 0.02. Or for concrete, we will say 4%, 0.04. So even 0.1 is larger than most of the numbers we work in regular structures. If some structure have base isolation or additional damping systems, then yeah, it may go up. The damping ratio may go up to 10%, that is shown here, or 10, 20%. Critically damped, where the damping ratio is 100%, and over damped is not really related to structural engineering, what we do. So we just show it here and we don't deal with it. And all our work is with underdamped systems. So this is the definition. I will talk a lot about damping ratio. Again, something to bookmark in your reference book or in the slideshow, but nobody expects you to remember this equation. You must know for many years of working as earthquake engineer is that what is the damping ratio of your structure? The fact that because of that damping ratio, your vibration will be damped out. This equation is resolved here. Probably I copied it from Chopra. And Chopra mentions that when you have damping in the system, your period slightly changes. However, as I said, for the real structures that we work with, this zeta is 0.02 or say 0.05 maximum. And if you work out this equation, you will see that TD is almost identical to TN. And practicing earthquake engineers, we don't have different T's, we only have one T. So we have the period of the structure. We even forget a lot of time that there is a very minor difference. We only use TN. But then for the people who are even more interested. Okay, I have copied this statement probably from Chopra itself that even when you go as high as 20% damping, which means like you have used serious dampers, you have built up serious dampers into your structure, still WD and WN or TD and TN are almost identical. So that's why like in practice, we can forget about any difference because there's no difference. Example, damped response, yeah. 2% reminds me of steel, so it will gradually damp out. 5% reminds me of, say, concrete, lightly reinforced concrete, where there is more cracks. 10% is probably you have some dampers in the system, like some artificially built dampers, I mean. And 20% you have a lot of artificially built dampers or base isolation, etc. So in a lot of real structures, we are in one of these two, 2% or 5%. But it's good to have this in mind that when you have higher damping, the motions will quickly damp out. That's what we call it, damping. They damp out the motions in a way. Log decrement method. This is a very, I think it's like if you are more specialized in earthquake engineering, I don't know how much you probably cannot guess how much specialized you will be in earthquake engineering. This one is important. So you sometimes need to estimate of the damping of your system just by looking at this like a very back of the envelope calculation. Although I keep on forgetting the equation, but again, I have bookmarked my Chopra so I can find it quickly. But you want to do a quick back of envelope calculation of your system damping. You have created a or the person who works for you, they have created a very sophisticated model of a dam and foundation and water and everything around the dam, and there are contact surfaces, etc. And I asked them, okay, so what is the system damping? What is the damping of the whole system? There are more sophisticated ways, and I will show that to you. However, this is not sophisticated. So I'm the analysis person, so I talk a lot about analysis, but there are like experimentalists as well. Maybe you want to just give a shock to your dam and then measure your basically damping. So in both cases, in say numerical model in your finite element tool, you apply a load to the top of the structure, in my case dam, and then let it damp out. There will be free vibration and motion damps out, as we discussed. We can use this solution here to quickly estimate the system damping. And yeah, so this is again from Chopra. There's the more sophisticated equation, which is different than the simplified equation, this linear equation. Again, between 0% and 20%. 20% is very high damping. These two, we cannot recognize one from the other. So use the simpler one. Calculate this delta, the logarithm of the ratio of U1 to U2, and then calculate your damping value. This quick estimate also gives you a quick estimate of your system period as well. You just measure the time interval between this point, and that's a good estimate of your period. Again, this works both with modelers and experimentalists. So it's a very good, easy tool. Yeah, so I copied free vibration testing in real world. Free vibration test can be applied to a structure by pulling, releasing, or shaking, stopping, measuring the free vibration response, and then determining of frequency or period, as I said, and damping. Again, as I showed here, I showed the damping here because it's a more sophisticated equation, slightly. And the period, which is just measuring the interval from, say, this point to this point after a full movement. Picture Golden Gate Bridge. The fundamental natural bridge with the main span of 4,200 feet was measured to be 18.2 seconds for transverse vibration, like sideways, 10.9 for vertical, and 2.81 for longitudinal, means along the bridge. And then 4.43 for torsional if it twists. These vibration properties were determined from recorded motion of the bridge under ambient condition. So we said that we can apply a load to the structure. However, I mean, San Francisco is super famous for the wind, and there is no lack of wind there. So when the wind gust happens, the structure deforms and then it starts vibrating, and then engineering firm can do their measurement and plot this curve and obtain both the frequencies of interest and the damping of interest. Again, you can do that in the lab. This is in the University of Western Ontario in Canada. So common requirement for non-structural components. I have seen that sometimes when like it's part of the spec and you want to purchase an electric tool or mechanical tool, they should have done this test on that tool and they tell you about the different characteristics of that equipment that you want to install, say, on your dam or in the industrial building. Less common to test full-scale structure. Application of load is difficult. Yeah, we will do that test. Hopefully this year we have success. We can show you the that shaking table. There is a small structure in there, and we can show you. We can complete a free vibration testing. That can be done using shaker and building up amplitude and then stopping to achieve free vibration. So they also have a shake table. They apply some shake and then stop shaking, and structure will keep on moving. Okay, so this is completing free vibration. Tell me if you have questions. Let me open the chat. Sometimes something comes in chat. Looks like we are okay. Okay. We continue with ground motion excitation. Ground motion excitation is like the real earthquake. Most solutions are developed for the loads or initial conditions which are applied at the center of mass. We discussed that. So we assume that the whole mass is on top of your portal frame, and exactly equivalently, instead of applying the base vibration, base excitation, we apply the load on mass. So that's the real, what really happens, which is base excitation at the base versus what is exactly equivalent. There is no simplification in that to apply varying force, the force that changes with time to the mass. So again, here in the real earthquake case, we have base excitation where the whole ground is shaking and pushing the structure back and forth. In the modeling purpose or in the structural engineer's mindset, we have a force that is applied to the mass. And these two are, as far as we are concerned, as a structural engineer, they are identical to each other. And what is happening is that, so there's no, like, in reality, in real life, there is, when earthquake happens, you don't have any forcing function. All you have is accelerations. So you have this inertia term, you have the damping term, and you have the spring term. All forces cancel each other out, and there is no external force. However, the inertia part could be divided into two parts, which is because the total acceleration that your mass is seeing is its acceleration with respect to ground plus the ground acceleration. And when you insert this in here, and you can take this term to the opposite side of the equation, and you have this equation. Now it's as if you have a forcing function. And as I told you, this is like mathematically, it's equivalence. So we are not simplifying anything. We have, as far as like this dynamics of a structure's solution is concerned, having this system is equivalent to having this system, where the base is stationary, it's not moving, but the forcing function is changing. And here it's called effective earthquake force. Like effectively, there's a force applied to your mass. Moving forward, harmonic excitation. The plot shown here is the forcing function. So the forcing function that we were discussing about, we mentioned it a few times. So this is not displacement, this is forcing function, and the forcing function is harmonic. We call it harmonic. It has its own period, forcing function period, different than the period of a structure, or maybe they are the same, or maybe they are not. That forcing function changes in time and increases and decreases, like it's a back and forth force. Consider a system excited with a harmonic or periodic force. Alternatively, the structure could be excited with a harmonic base acceleration. As we said, there are identical issues, either base acceleration or the force. A new parameter is introduced, which is the excitation frequency, which obviously can be different than the natural frequency of the system. I said that. How the structure responds now will depend on all the same parameters as in the free vibration, but also on the amplitude and frequency of the excitation. So you have the same scenario as the free vibration, but you also have a forcing function, which is harmonic itself, meaning that it keeps on being the same shape. Force vibration, harmonic, mathematical calculations here, which like you can go through depending on how deep you want to go into dynamics of a structure. However, I suggest that everybody carefully look at this plot, which shows the response with time. So the response will have two components. Like here we have an equation for the response. It has a transient term and it has a steady state term. Here we have shown the total response, which is U of t, and we have shown the steady state response, this term, and the difference of the two is the transient one. Transient means that it will damp out in time. So it's depending on the damping of the system, and it will die out or it will dissipate. As you see, the transient part dissipates after, like in this case, it's not second, it's after a few back and forths. Like it is calibrated with respect to the period of the system. Oh no, it's calibrated with respect to period of the forcing function, actually. The transient portion will gradually die out. However, the steady state response, which is directly affected by the forcing function, it will persist because the forcing function keeps on forever pushing the structure from one side to the other side. The transient portion will dissipate. So that's something to really learn from this slide, is just this plot. And this is for the people who will do their project or their research on this subject. Let's see what this plot shows. On the horizontal line, it shows the frequency ratio, meaning the ratio of the frequency of the forcing function divided by the frequency of the system. And on the vertical axis, it shows deformation response factor, which is a measure of the, like a calibrated measure of the deflection. It's calibrated with respect to equivalent static movement. Like, what if you apply that load not in a harmonic way, but in a steady way? But you don't need to go that deep. Just vertically, we have a measure of the responses that we see in the system. Horizontally, a measure of the frequency of the input. And as you see, when the frequency of the input, or what I call input, means that forcing function changes, the response might change a lot. So the frequency of the forcing function is important. And again, back to the discussion that we had maybe 1 hour ago, the frequency content of your earthquake is important, and it causes a lot of change in the response. So let's study further these 3 regions that are in a way highlighted, starting with this one, the middle region, is when the frequency of the input is almost the same as the frequency of your structure. What happens, we call it resonance. Resonance means that your earthquake has almost the same frequency content as your structure's primary frequency. So the resonance happens, and you see huge response. So that you have the most response when you have the greatest response, when the frequencies are very close to each other. And you see the effect of damping. The numbers for each curve is damping. When you have larger damping, like these damping values are not of interest to structural engineers. Let's start from 0.2. When you have a larger damping, your response is, it's resonated, but not by much. When you have 0.1, 10% damping, the resonance effect is greater. When you get to 0, which is not real, not physical, if you have no damping in the system, the resonance effect could be infinite, like it should be very, very, very large number. Even with 1% damping, you see that the resonance effect is large. So that's the resonance effect. When the input frequency is very small, that's the first line here, meaning that, practically you are static because it's not really vibrating. And the frequency is very small, and the changes are happening in a very, very large period. So practically you have a static response. At the frequency of 0, your response is your static response. And when your input frequency is very, very large, that's the second line here, rapid response is mass controlled, meaning that the response is this value. It could be simply calculated. I don't think it's of interest to us in earthquake engineering, but it's a system which applies the load with very high frequency, and stiffness doesn't matter, and it's mostly controlled by the mass. While in the static is previous courses that you had, the response is mostly static. And our range of interest, maybe in earthquake engineering, is somewhere in between. We try to avoid resonance, obviously, because resonance means huge response. And now, other more sophisticated, better solution for calculating the damping of the system and also the frequency of the system in this method, which is called half power bandwidth. I quickly explain it. You need to be aware of this solution, maybe use it in project or maybe in your future work as a more advanced earthquake engineer, technically higher ranking earthquake engineer. And in this solution, what we do, again, you can interpret it both in the experiment and in numerical tool, analytical tools. You have your structure, you apply a harmonic load to it with certain frequency, and you change the frequency of the harmonic load, and you note down the maximum response. As we saw here, when we reach the frequency of the structure, the response becomes maximum. So here is where you can measure the frequency of your structure. That's where the applied harmonic frequency of the load is the same as frequency of your system. And there is this fancy solution to better measure the damping of the system, which in terms of steps is that you draw this plot, you measure the maximum response, multiply it by or divide it by a square root of 2. And you come here, and the distance between this point and the horizontal line is 2 zeta, and which is called half power bandwidth. So basically, you measure the distance meaning in terms of frequency ratio from here to here, and you divide it by 2, and you have your damping ratio. That's a more accurate way of calculating damping ratio or measuring damping ratio, comparing with the free vibration. Again, the equation is here that I just mentioned. So in terms of the steps, in a way or other, like you have your SAP 2000 model, you analyze it, say, 20 times, and then you come up with this maximum responses depending on the loading function frequency. And now you have the primary frequency of the system. Divide this length by a square root of 2, and then you get your 2 points, FB and FA. FB is the larger one, FA is the smaller one, and it's calibrated because this axis is calibrated and divided by 2. That's the half power bandwidth solution, which is a very strong tool in determining the damping ratio of your system. Now, discussion on single degree of freedom response. In free vibration, with an initial displacement and velocity, the system will oscillate at the natural period of the system, and the oscillation dissipates proportional to the damping or damping ratio. Externally applied loads will add an additional response. Again, with good engineering judgment, all are agreeable. In the case of harmonic loads, the structure steady state response will be at the applied load frequency with a sustained amplitude. That's what we showed here. So the steady state response keeps on repeating itself. The transient response will die out soon after a few back and forths. Earthquakes are not harmonic loads and need to be treated differently. Therefore, solutions should be obtained by numerical methods, meaning more accurate solutions need better numerical methods, which are applied in, say, finite element method in SAP 2000 or finite difference method in other applications. End of this part. I think we are almost at the end. So let me not proceed. Yeah, we have 3 more minutes. 3 more minutes. So let me open the chat. Yeah, it's time for you guys to ask your questions, concerns, or even discussion on the project, creating teams, etc. We have about 3 minutes. Can we have a group of 5? Yeah, I mean, we have had groups of 5. I don't recommend it. Try to avoid it. And if you have a group of 5, really show in your scope that you have enough tasks for 5 people. So yeah, you can have it, but be careful. Like maybe we go more iteration with your scope, meaning your work plan, showing you must show to us that you have enough tasks for 5 people. Okay. Okay. Any more questions? What is the time? Okay, we have 1 more minute. That's fine. If there's no question, then I will try to close off. Hopefully, everybody has a very good week ahead. I will talk to you guys on Friday. Please talk to each other and form up your teams. See you guys soon. Stop share maybe. And close everything.